Perhaps one of the most important skills we'll learn in physics is problem solving. The steps we're about to learn might be slightly different in a different textbook or a different class. So you'll learn problem solving in a chemistry class, you'll learn problem solving perhaps in an engineering class. And if you go into the business world, you'll learn problem solving there as well, especially in a management course. And the steps you'll learn in those courses will be somewhat different than the steps you'll learn here. But underlying those variations, you'll find the same basic idea behind solving the problems. And so this problem solving skill that you're going to learn in this physics course really is universal throughout any subject area or any business area that you might go into. And so this is arguably the most important skill that you'll learn and practice throughout the rest of this course. So the steps might be outlined as you'll see them here. The first step is to read the problem. Now, reading the problem might sound very simple, but it's a start. You have to start by reading the problem and looking at all the information that you've been given when you go through that problem. Keep in mind some of the information might be stated without being stated very explicitly. For example, if I say that I drop a ball off the top of a tall building, the word drop means to let go of with no initial speed. You aren't throwing it down, you aren't tossing it up and then letting it fall. When you drop it, there's no initial speed given to that ball. That piece of information is critical, and it's in the word drop. So you have to be able to find that kind of information as you read the problem. Your next step is to identify any of the given values. For example, in our first problem here, to drop a ball, that initial speed of the ball is 0. But you might also be given the height of the building. You might be given the acceleration due to gravity. You'll probably not be told that there's no air resistance, but you're going to make that assumption unless it specifies that there is air resistance. So in this physics class, we want to keep things as simple as possible without making them too mundane. So the given values are the pieces of information that you know. And you probably want to write those things down symbolically and with the values that are given, the numeric values. Next, what is it you're looking for? What is it we're trying to find? So there might be more than one variable there. I might want to know the time it takes for the ball to hit the ground, and or I might want to know what's the speed of the ball just before it strikes the ground. To accompany this problem solving, we oftentimes want to draw a picture. A diagram or a picture can be very helpful when solving the problem. Again, there might be pieces of information in that diagram that you're going to need. So draw a diagram, and usually I recommend you draw that diagram large. If you have access to a whiteboard or a chalkboard, take advantage of that and make the diagram significant so that you can really utilize it to the best of your abilities. Then you want to ask yourself, what principles am I going to need to solve this problem? Now, if you're working problems out of the chapters in the book, then the chapter is probably going to have all of the principles that you need in order to solve the problem, although you may also need to use information from previous chapters. When you're on an exam, especially the final exam, you have a lot of information that you've been taught over the course of the semester or the course of the year. All of that needs to come together in order to solve that problem. You, as the student, need to discern what principle or principles am I going to need to solve any one of these problems. Keep in mind also, there may be more than one principle that you can use to solve the problem, but one of them might be easier to use than the other, and that may vary from one student to another. Once you've identified the principles, you want to ask yourself, what are the equations that I associate with those principles? And you want to write out those equations using the same symbols that you may have used when you identified your given values or identified what it is that you're looking for. So by using the same symbols, you're going to be able to fit the numbers into the equations and solve for that final unknown or unknowns. So examine the equations, match your known values and your unknown values with the equations that you have. Keep in mind you must use only equations that are valid for the specific problem. One of the biggest mistakes we see in physics and engineering are the kinematic equations you'll learn in a few weeks. These equations are valid whenever the acceleration is constant, but there are many, many cases where the acceleration is not constant, and yet students will continue to try to use constant acceleration equations when they're solving for those problems. So be very careful of that. Once you know what it is your unknown is, and again there may be more than one, solve the equations from the previous step algebraically to find that unknown. I recommend you do this algebraically because if you make a mistake in the algebra, it's easier to find than if you make a mistake in calculations. I know the algebra might be a little bit more difficult to go through, but in the end, you're going to have a much sleeker and better answer if you go through them algebraically. Once you have that final equation, then plug in the numbers that go along with all the variables or all the values in the equation, and then do your final calculation. Once you've got that calculation, you need to determine whether or not it's reasonable, and this is a very important step. For example, when you're solving a quadratic equation, maybe for time or for length, you might end up with a positive and a negative answer. In that scenario, you have to ignore the negative answer because you can't have a negative time or a negative length. Algebraically, that answer exists, but in the physics of the problem, the answer is not sensible. You also want to look at the numeric values. If I'm talking about the speed with which somebody is walking and I end up with 20 miles per hour, then I'm pretty sure I've got a problem somewhere in there, and I've got to figure out where I made that mistake. When we get into the section on units, that's going to be one of the biggest things that you can do is utilize your units wisely because they'll oftentimes tell you whether or not your equation is right or wrong. Okay, so let's take a look at a simple problem. This is going to have to do with a mountain bike, and what we're given is that the rear sprocket, and it could be any one of these, has 14 teeth on it. Okay, so we're going to measure the circumference around that sprocket in units of teeth, and the reason that we do that is because the spacing between teeth on the front and the rear sprocket and on the chain is the same. So I have a rear sprocket with 14 teeth and a front sprocket here with 42 teeth. And I believe there's 44 on this diagram, but let's assume 42 teeth is the number on that front sprocket. What I'm interested in is if I rotate the pedals, which are attached to the front sprocket, one full rotation, then how far has the tire gone, which is attached to the rear sprocket? So my given information is that the circumference of the rear sprocket is 14 teeth, and the circumference of the front sprocket is 42 teeth. I'm also given the diameter of the tire is 29 inches. What I'm looking for is the distance x that the bicycle has traveled. The principles I'm going to use to solve this problem have to do with rotational motion, which we'll get to in more detail later on in the course. But just keep in mind what you do know about the rotation of your tire. And then we're going to look at some relationships between gears. And the main relationship that we're interested in here is that the linear travel of the chain between one sprocket and the other, if it travels a distance L here, that's going to be the same arc length here and here. So the arc length for the front sprocket, for the rear sprocket, and the length of the chain that's traveled are going to all be the same. We're going to really need to take advantage of that. So 42 teeth is equal to the length of the chain because remember that the front sprocket has gone through one full rotation. So the arc length, sometimes written as S equals R theta, where theta is the angle through which the circular object has turned, and R is the radius of that circular object, in this case the front chain. The arc length S is equal to R theta. Now, that's the circumference of the front sprocket, but it's also going to be the distance, the arc length, through which the rear sprocket has traveled, also the length of the chain, but we're mostly interested in how far has the rear sprocket traveled. So what we're going to know here is that some number n, and I'm not sure what that is yet, some number n was the number of times the rear sprocket has turned while the front sprocket has gone through one full rotation. So the circumference of the front sprocket is equal to some number n times the circumference of the rear sprocket. So I might write c of the front sprocket equals n times c of the rear sprocket. And now I have a very simple equation, so I'm okay to put some numbers into these variables. So 42 is the circumference of the front sprocket. 14 is the circumference of the rear sprocket. I might also have written n, the number of rotations, equal to circumference of the front sprocket over the circumference of the rear sprocket. And in this scenario, I find that n is equal to 3. So the rear sprocket has undergone 3 full rotations, while the front sprocket has undergone 1 full rotation. Now keep in mind the tire is attached to the rear sprocket. So if the rear sprocket undergoes 3 full rotations, the tire must also undergo 3 full rotations. And so the distance the tire traveled, x, which is what I'm looking for, is going to be 3 rotations times the circumference of that tire. And the circumference of the tire is equal to pi times the diameter. So this would be n times pi times the diameter of the tire. And we know the diameter of the tire is 29 inches. And so 3 times 29 is 87 times pi. And if I multiply that out, I'll get roughly 270 inches. And I say roughly because pi is an irrational number, and therefore I must have rounded off.